Hello everyone, welcome to the IoT demo. In this session, we will be introducing the Carleton-Cisco IoT testbed by going through its architecture, features, and applications. This work is presented to you by the Cisco Chair team at Carleton University Internet of Things Lab. The IoT lab is directed by Professor Mohammed bin Kahla, an NSERC Cisco Industrial Research Chair in IoT. I am Ziad Bouida, Senior Researcher and Cisco Chair Technical Manager. Also presenting today, Ismail Al-Shayab, Yusuf Rafiq, Abdullah Jarwan, Sajib Kumar Khoury, who are PhD candidates with the IoT lab, and also Manish Kumar Murjamalani, a research assistant with our lab. We want also to thank other team members who are not presenting today and who are contributing to the IoT testbed, including Dana Haj Hussein, Uthman Al-Aiduris, and Abdullah Mahmoud. The presentation is organized as follows. After an introduction of the IoT testbed, we go through its architecture, components, and features. Then we present selected IoT applications and demos of the IoT testbed. This includes the smart grid communication and analytics, smart gardening, intelligent transportation systems, and data analytics at the edge using the information-centric data reduction. Before concluding, we present the data management and visualization process. The Carleton-Cisco IoT testbed adopts a layered approach with four main layers: sensing, edge computing, fog computing and core network, and cloud layers. It also supports the cross-layer nature of the IoT and thus enables system design and data processing at all of these layers. As we will see from our applications, the IoT testbed offers accurate multi-user evaluation tools over heterogeneous networks and technologies. It also considers the complete cycle of IoT, starting from the design, development, and deployment of IoT application. In what follows, we will start with the IoT testbed architecture with Ismail Al-Shayab.
In the following slides, we present the testbed architecture, components, and features. First, we start with a description for the general testbed architecture. As can be seen on the right side and within the large black rectangle is the IoT research lab inside Carleton University campus. On the top of that, different IoT and user applications could be deployed with the help of the public cloud in the different fields including smart home, smart grid, intelligent transportation, smart hospital, smart gardening, and public safety. In addition to the sensor networks and IoT applications deployed within the Carleton University campus, multiple other applications are deployed within the city of Ottawa in the context of a smart city and that are accessed remotely for management. In addition to that, data is being collected and integrated to the full system using the public cloud. In more detail about the layers, the sensing layer includes different and heterogeneous set of sensor networks that use different access technologies to push the sensed data to the edge computing layer. The edge computing layer spans in different buildings, including Mackenzie Building, Arise Building, which is one of the new smart buildings within Carleton University campus, and other buildings. The plan also is to expand into different other locations. Also, the fog computing and private cloud layer is deployed in two buildings, which are the Mackenzie and the Arise, within the main server's rooms. These locations include high computing workstations and servers that see larger scope of data and that also could do tasks that require higher computing resources. Centralized controllers, including software-defined network controllers, also network function management and orchestration, are efficiently deployed in the fog computing layer. Regarding applications, they are built all the way on the top of the edge computing layer, fog computing layer, and also private cloud and public cloud. These applications can be in the different scopes and areas of Internet of Things, but definitely they would require different computing resources, and also they require different scopes of data. A second view of the architecture is presented here that focus on the different functions and features. In a similar manner, the IoT research domain is presented on the right side within the dashed blue rectangle. This includes the main layers of sensing, edge computing, fog computing, while the cloud layer comes on the top of the previously mentioned layers. The communication between the different IoT applications and sensing domains within the IoT research lab inside Carleton goes through the Carleton campus network. In addition, the data going from the IoT research lab to the cloud and the configuration posted from the cloud are also passed through the Carleton University campus network. Carleton University campus network is shown on the left within the light blue rectangle. Cisco is working with Carleton University to equip their infrastructure with one of the promising and advanced platforms called Cisco Digital Network Architecture, or Cisco DNA for short. This platform is built on the top of a software-defined access fabric and is central management and automation for large campus networks. Features like the provided APIs within the DNA are used to support IoT application with network stats, statistics, device registry, access control, and device management and configuration. To shed some light on the different functionalities, a color code is shown on the right. The network management blocks are shown in the pink color. The service-related blocks are shown in purple, applications in green, while infrastructure-related blocks are shown in orange color. The network management blocks spans through the different layers and includes functionalities like device management, IP management, device availability, and also the cybersecurity requirements, including access control, authentication, and trust management, just to mention a few. The service-related blocks are services and functions that are required to keep the testbed running properly and also to keep the application in healthy status. These services also spans in the different layers. So for example, data generation, environment control and automation in the sensing layer, container-based and edge load balancing, traffic analysis, resource allocation in the edge layer, brokers, and local database logging in both fog and cloud layer. From the management platform point of view, the Cisco Field Network Director (FND) and also the Cisco Kinetic Gateway Management Module (GMM) are used for remote management and Docker's deployment. Applications are highlighted in green and they can be deployed all the way on the edge layer, on the fog layer, or on the public cloud. The diff applications can be deployed in the different previously mentioned IoT areas, for example, video processing, big data analytics, artificial intelligence, automation, etc. So many applications were mentioned previously. These are just some examples to shed some light. Last and not least, The infrastructure-related blocks are the ones related to the hardware and devices. And this goes also through all the layers. More details will be shared in the following slides.
According to functions-based architecture, there are 4 layers in Carleton-Cisco IoT Testbed, and different Cisco and non-Cisco devices are connected in each layer. Starting from sensing layer, data generation, analytics, and data aggregation through wireless sensor networks are done in this layer using Raspberry Pis and Arduinos. In the edge layer, data collection, edge computing, data analytics based on application requirement are done through Cisco devices including IR829, CGR1120, etc. And functionality of these devices will be elaborated in next section. Fog layer act as a local cloud in our system. Edge data analytics and application provisioning through local management is done in this layer using Cisco UCS 240 and Dell Precision servers. In the cloud layer, IoT applications and API management is done through global access or public cloud. Edge data analytics in public cloud is done through AWS Kingsford.
IoT testbed Cisco devices in edge and fog layer are shown in this table. First 5 devices are using in the edge layer and last one is using in the fog layer. Starting from industrial router IR829 is used to deploy a wide variety of IoT solutions based on applications. This device is capable of doing asset monitoring and device management. Industrial router 1101 is highly modular and has more computational power than IR829. We use it for applications which needs more computational and processing power. It supports expandable delivery and unified management for distributed IoT deployment. Industrial Compute Gateway IC3000 delivers on-demand computational power for IoT applications and data analytics in real time. Cisco Catalyst IE3400 used to manage through Cisco DNA Center, which is currently in progress to implement in the university network. IE3400 also used to real-time traffic pattern visibility and threat analysis. Connected grid router CGR1120, which is indoor one, and 1240, which is outdoor one, are used to translate application protocol. Also supports distributed data processing and application security in the edge. Unified Computing System, also called as Cisco UCS Server, is the fog layer device in IoT Testbed to aggregate and store data locally, and also performs edge analytics.
In Carleton-Cisco IoT Testbed, these applications are running currently, which includes Smart Grid, Smart Gardening, Smart Patient Room, Intelligent Transport System, and Smart Building. Starting from Smart Grid supports appliance health monitoring, power consumption prediction, and usage reduction. Smart Gardening is capable of doing automated crop monitoring, gardening parameters such as water level, light, humidity, and temperature control. Smart Patient Room is used for health monitoring, alarm system automation, and private edge analytics. Intelligent Transport System controls and optimizes traffic flow dynamically. It also used for faster emergency response and traffic reroute. Smart Building processes automated appliance operation, smart decision making, data collection, and analytics. In next section, we will discuss about applications in details, including some demo.
The first application we show here is the Smart Grid Data Communication and Analytics. We first show the system architecture of the Smart Grid Data Communication System. So we have a home referred to as Customer Agent or CA that has multiple appliances managed by the Home Energy Management System. And that Customer Agent is establishing a communication with the Transformer Agent at the neighborhood. In our lab, we take care of this communication between the CA and the TA, actually between different CAs at different homes and the TA. Now, sometimes it's not possible to establish a direct communication between all homes and the transformer agent. So what we did, we developed a mesh network that enables all homes to communicate with the transformer agent by using other homes as relays. Now here we took into consideration about the communication reliability, delay, and most importantly, the cybersecurity aspects. Here we show the smart grid data analytics system architecture. Basically, we consider multiple neighborhoods where the data from different CAs is sent through Wi-Fi mesh to the TA of that neighborhood. And that TA, we use here LTE for that TA to send the data to the back office. In the back office, we consider IBM Cloud in order to deal with data. And this is explained in this slide. So starting with the data pre-processing, we have different steps, including resampling, aggregation, removing any irrelevant values, and handling any missing values in the data communicated, and then remove correlated features. 3 other steps with the feature extraction, scaling, and selection. And at the end, we are ready to apply the prediction model. Now, for the prediction model, we have different granularities, the daily prediction or half hourly or other types of predictions. And the scale of this prediction will depend on how far we want to go in the training data in the past and how much data are we planning to predict in the future. Now, in this slide, we present selected prediction results. In the upper figure, we present the electricity in watt-hour in variation with time for both the actual data in turquoise and the 3 prediction model we use, namely the long short-term memory, the support vector regression Gaussian model, and the ensemble model, which combines the power of different models in order to improve the results. So talking about results and measuring the efficiency of different predictors, we use 3 error performance. One of them is the normalized root mean square error. And as we can see here from this figure for the NRMSE, we have a better performance offered by the ensemble model. Coming back to our main architecture, here we summarize that the smart grid application is both running externally in real homes at the city of Ottawa, and we do also use our nodes to simulate appliances at Carleton University. And then we have this running both at the edge and as a fog. Now we go to the next application.
Now let's talk about smart gardening application, which is one of the use case of Carleton-Cisco IoT testbed. First, system architecture and data flow. Now as you can see in the top left corner, there are sensors, energy harvesters, microcontrollers and actuators which help system generate sensing data, do threshold comparison and actuator control. With the help of router, data is now transmitted to public cloud. Using ThingsBoard, user can set SMS or email alerts depending upon usage. In the bottom, you can see components of sensing nodes, which includes sensors, analog to digital converters, microcontroller unit, which is Raspberry Pi here, actuators, energy harvesters, and battery, which helps system to sense data and do energy management. Now let's see decision making at sensing node. It reduces lag between sensing the data and actuator control. The process starts with loading up the set values of different environmental parameters received by either from public cloud or old set values stored in system. Then system chooses action for different environmental parameters, such as if the set values received is for soil moisture, then sensing node compare its set values with sensed value of soil moisture sensor and decides the action for water valve. Similarly, action taken for fan or heater depends upon comparison between sensed value of temperature by DHT22 sensor and set values for temperature. Finally, the operation of grow light depending upon direct sunlight available here sensed by LDR and how many hours of grow light is required by the plant. At the end, all the other sensed values by different sensors like PIR, gas sensor, rain, humidity and SOC percentage means battery power remaining sensor and the state of actuators is converted into JSON file. Then this JSON file is published to cloud. This cycle runs automatically unless until interrupt occurs. Hello all, this video will be demonstrating the prototype of the smart gardening application, which is one of use case of Carleton-Cisco IoT testbed. This prototype is mainly consisting of 4 components at user end, as you may see: one microcontroller unit, sensors, actuators, user interface. As observed here, a user can monitor and control different environmental parameters such as temperature, moisture, and light with the help of IoT testbed. First, set values for each parameters are assigned using ThingsBoard, then comparison of these values to the sensed values is derived by Raspberry Pi. Set values are received by sensing nodes from MQTT Cloud, which is hosted by IoT Lab at Carleton University. Taking an example, the room temperature here sensed by DHT22 sensor is around 22 degrees Celsius. If now user changes the set value for the temperature below room temperature as shown, the fan will be turned on to cool down the area. Similarly, the supply of water can be monitored and regulated. As seen, the current value of water level in soil is around 48%. If the set value for water is increased to 63%, then water valve will be turned on. Water valve will turn off once required moisture level is achieved. Finally, the operation of grow light in the system is dependent on the availability of direct sunlight. If the sunlight is insufficient, then system will turn on the lights to provide required grow light for the plant. Sensing nodes monitor duration of the direct or indirect grow light available. As you may notice, the set value for this system is set to 10 hours of light for entire day. This can be altered as per plant's need. All of the rest sensed values of environmental parameters that can provide users important information about plant's health as well as system's health, such as different gases level emitted by plant, amount of luminance received near plant, humidity in the air, proximity detection, rain detection, and power remaining in battery. With this IoT testbed, user can also create, store, and analyze database collected by the system over the period of time, which can be very useful in further advancement in plant growing patterns. Finally, this slide shows general architecture for testbed covering parts of smart gardening application only.
Now, we move on to the Smart Intersection Control Edge application that falls under the Intelligent Transportation System umbrella. The Smart Intersection Control System is made up of two main components, the video processing part and the traffic light control logic. The video processing component is based on OpenCV open source library. It does two main things, lane and car detection and vehicle counting. Based on the video processing component's inputs, the traffic light control logic composes of a smart lightweight algorithm that is designed for managing and controlling the traffic lights based on vehicle count. Both components are packaged in Docker containers for portability and ease of deployment. Because they are packaged in Docker components, we can easily deploy them on any nodes in our system that are computationally capable and are at the network edge. Now we discuss the system model of a miniature traffic intersection deployment in our lab. As shown, we have traffic flowing in the north, south, east, and west directions. We have traffic lights connected to a Raspberry Pi and IP cameras mounted at each direction. These cameras communicate wirelessly with the edge gateway. Additionally, a Raspberry Pi 4 is deployed at the edge. Camera feeds are streamed via wireless gateway and flow through the Raspberry Pi using real-time streaming protocol. The Raspberry Pi hosts the video processing logic and the traffic optimization logic. It processes the video streams and determines the traffic light control parameters to be sent back to the traffic lights. The traffic parameters are communicated from the Raspberry Pi 4 through the IR829 gateway wirelessly back to the traffic lights using MQTT protocol. Finally, a visualization server is deployed to monitor system behavior. Now we discuss the system's operation. The system requires a video source as an input. It could be live traffic stream or could be pre-recorded videos. Each video is converted into a series of frames. After capturing a single frame, various image processing techniques are applied to each frame, including filtering, noise reduction, and object detection. Now you can see the processed video stream that captures the number of cars flowing in a particular direction and their count accounted for in each lane. Finally, we saw the system in operation. As cars approach the traffic light, the camera stream is processed and traffic is detected. Based on the incoming traffic, traffic lights turn green. Referring back to the original architecture, the Intelligent Transportation System application uses the sensing layer, the edge computing layer, and runs entirely at the network edge, where the sensing layer is composed of custom sensors, surveillance cameras, and traffic lights that push their data to the network edge, and at the network edge we conduct analytics, storage, and network management.
In this part of the presentation, we will discuss edge data analytics and we will present an example on that.
The developed testbed also employ data analytics on the edge, more specifically at the edge Cisco routers. Usually the edge is used to run a part of user applications, such as running alarms and actuation. It also enables running delay-sensitive applications closer to the edge. On top of that, the edge is used in analyzing IoT traffic in order to manage network resources.
It can be used to enhance resource utilization, and it can be also used to reduce IoT traffic, which leads to better network performance. As an example on edge data analytics, we have used edge routers to evaluate the information content through the incoming data streams. The information content is evaluated using the probability distribution of the data through the stream. When a new stream arrives, there will be no probability distribution built, and the information content is therefore high. As the stream continues, data may become repetitive and highly probable to occur, which result in having a continuous drop in the information content. When a sudden change occurs in the sensed environment, the data becomes very difficult to predict due to their low probability to occur, which result in having a high IC. As the stream goes on again, the information content starts to drop because the data becomes repetitive. The information content concept is implemented to reduce the amount of data that the edge devices forward. Wireless sensor networks generate data and send it to an edge device. The edge device then buffers the incoming data, and based on the history, it evaluates the information content of the received data. If the information content is higher than a predefined threshold, we consider that this data is not redundant and cannot be easily predicted, and the edge device forwards it to our cloud infrastructure. The edge device suppresses the data that has low information content, which improves resource utilization. As an illustration for the information content-based data reduction, the blue curve in this figure shows the sensed data stream that are being generated by a sensor node over a period of time. The yellow curve shows how the information content is changed over the data in the sensed stream. We can see that when a sudden change happens, the information content goes up. The green data points show the data points that are received after reducing the data at the edge device. Using simple interpolation technique, the reduced data can be accurately recovered. As another illustration of the information content-based reduction scheme, we can see in this figure the generated data stream and the received data stream. As we can see by the chart, we have achieved around 80% data reduction. This leads to having a better resource utilization at the network while saving resources. In summary, this figure shows the implemented data analytics in our testbed. The data generated at the sensing layer and collected at the edge devices is reduced and analyzed in order to save resources at the fog, network, and cloud layers, while the data is being transmitted from the edge to the AWS cloud.
Now we move on to the final part of our presentation, where we look at data management and visualization and present to you a demo. Before we jump into the demo, we need to discuss how the data flows through our system. Sensed data originates at the mesh sensing nodes. Shown on the bottom left, the mesh sensing network mimics a smart hospital deployment. These mesh sensing nodes are capable of relaying data among each other in a peer-to-peer manner. We chose this deployment scenario to address the challenge of limited range communications in geographically spread deployments. Next, data is transferred using secure copy protocol and hops between multiple nodes until it reaches the mesh gateway. The mesh gateway aggregates data from different nodes and does the necessary protocol translation. From this point forward, data communicates using publish-subscribe protocol, which is MQTT. Data is then forwarded to the Edge Compute Gateway using MQTT, where it receives data flows from multiple wireless sensor networks. The Edge Compute Gateway hosts an application container that enables data aggregation, encryption, and lightweight edge processing. Data is then communicated over the internet, where it reaches our cloud server. An MQTT data broker is hosted in the cloud and receives the data streams, and is assisted by a high-throughput Kafka message handler. A high-availability Cassandra database with multiple instances runs in the cloud and subscribes to the data broker, where the message handler decides which instance data should be forwarded to. Finally, data is visualized with the help of Testbed, which is an open-source visualization platform. In addition, system admins are able to use the power of publish-subscribe protocol and tap into any point in the wireless sensor network. They can access mesh nodes, mesh gateway, the Edge Compute Gateway, or the MQTT Cloud Data Broker to monitor and debug communications. We start with the wireless mesh sensing node that uses secure copy protocol to communicate between peer-to-peer nodes. It mimics a sensor deployment in a smart patient room. Characterized by small form factor and low power, enabling nodes to be operated by a battery pack. Each node is equipped with an array of sensors that monitor pulse rate, temperature, humidity, gas levels, and human presence. In the mesh, communicate with the wireless mesh gateway that does the necessary protocol translation from SCP to MQTT and does data aggregation. By using MQTT's publish-subscribe model, we are able to subscribe to any node on the network and monitor data flows that are passing through it. Next, we move to the Cisco IR829 Edge Compute Gateway that is responsible for encryption, data aggregation, and edge computing. It's equipped with a built-in access point that offers connectivity and is capable of hosting Docker-based applications. The gateway supports multiple input-output interfaces, including dual LTE connectivity, external antenna support, and gigabit Ethernet ports. Powered by Cisco Kinetic IoT Management Cloud, we are able to remotely deploy applications and upload them to the application library. Applications are selected to be deployed from the application library, and deployment configurations are set up here. Through the cloud, we are able to check the device status and monitor health of the applications running on each device. We are also able to monitor devices that are actively connected to the gateway's access point. Data is then aggregated to a centralized database and visualization platform that is supported by Testbed. Testbed offers us the capability of creating no-code dashboards and visualize IoT data in real time. As an example of system operation, here we show visualization of the pulse rate sensor that tracks vitals of a patient within a smart hospital room. The high-performance Cassandra database in the back end allows us to fetch historical data and quickly filter how far we want to go back in time. We can choose the last 5 minutes, the last hour, or the last few days. Dealing with real-time or historical data, we are also able to add statistics or conduct post-processing on the time series data. Now we look at another example that triggers the smoke alarm once abnormal gas levels are detected. Measured in parts per million, as we can see, the gas sensor is extremely sensitive to any change in the environment. As soon as smoke comes into contact with the sensor, gas levels spike. To better understand these spikes and when they happened, it's important to look at historical data. As shown on the graph, it's easy to spot the spikes that lead to triggering of the alarm. Gas sensor usually reports 0 ppm. However, at 5:41 p.m., abnormal gas levels were detected.
To summarize, the Carleton-Cisco IoT Testbed represents a state-of-the-art platform for IoT design, development, deployment, testing, and user experience. As we saw from the presentation, the testbed already involves many applications and real-world use cases, with several collaborations with industry and government. There are still great opportunities for research collaborations in many areas, including SDN, NFV, resource optimization, machine learning and artificial intelligence, and more. Thank you, and we open the floor for questions.